I'm going to do a quick introduction because I'm going to let Francesco speak for himself. But thanks everybody for coming. I know we're all recovering from AERA and NARS, and I appreciate you coming to another presentation. This is a really fun one because if you don't remember, I spent last year in Italy hanging out with Olivia Labrini's group at the University of Bologna, and I am really pleased and thrilled to introduce Francesco, who's a PhD student. Well, you tell your story.
Yeah, okay.
But I also am pleased to extend an invitation from Olivia. If you ever find yourself in Bologna, you should stop by the physics group and say hello. So, I asked Francesco, I learned so much being there about how Europe thinks about science teacher education and thinking about physics education as well. So I asked Francesco to sort of give an overview of what they think about in Italy in terms of science teacher education and physics, and also to talk about his research as well. I will turn it over to you. I'll take pictures for the video.
Okay.
There you go.
Okay, it's very nice to me to see you all here. I have to say this is my first time in US, so thanks for welcoming me. As David introduced me, I am a PhD student at the Department of Physics and Astronomy at the University of Bologna in Italy. So I will present here the broader. So what's happening here? Okay, I will present some general ideas about the context of research in science education, our approach in our research group, and part of my research, personal research within the group. And I will have some time, so please interrupt me, ask questions if you want to make me explain again what I'm explaining, or if you have some doubts, some suggestions, some comments. It's an open time, so we will spend together this kind of open time. So, as I said, I will skip this part. It was just some pics of me because I have some brothers. I am a musician. This picture is from NARS. I presented there last Friday, so maybe you were there also. I work as a social volunteer in social organization and so on. But my activity as a scholar is within physics education research. So, this is Italy, of course. And maybe you already have been there. These are the research group in science education in Italy. As you can see, we are not so many of them. We have just some groups, especially in the northern part of the country. So in Milan and Bologna, where I come from is Bologna. And then in Pisa, Rome, we have something, Naples, Palermo, and so on. And so, as you can imagine, there is not so huge tradition in physics education research. We are just 15 PhD students in all the country. So that's impressive to me compared to your situation. And most of the research groups deal with things like thinking about renovation of lab experiments within school, design of innovative teaching materials, the design of curricula, textbooks. And there are also different approaches in terms of techniques and methodologies. But I have to say that we have a kind of positioning that is quite detached from the global, from the country track of research. This is our leader, Olivia Lebrini. She's my advisor. And we are the largest group of research in Italy, 5 PhD. The total is 15, so 2 postdocs, 2 professors, and we are a kind of one of a kind because we have, you will see many projects going on and many funds and many people working there. So, this is our situation. This is us, the Bologna Research Group, and as you can see, I will tell, is Andrea Zanellati, PhD in Data Science Education, and we have 2 fixed research fellows in math education and in physics education. Giulia Taschia, she was at NARS too with me. We have a postdoc in physics education research, Eleonora, another one in physics education research, Sara. And then all the PhD students, me, Lorenzo, the other Lorenzo, and Emma. Martina, she's visiting from Oslo University, so maybe you know her. She's a psychology. She's Anna Harokenes, and this is us. So, something more about our situation in Italy, because I think it it could be interesting to you also to get to know the difference that we have between US and in Italy. So for example, we don't have college of teacher education or science education. So we are, for example, within the physics department, and also our other colleagues are within the physics department. But you have somewhere else also just courses on science education. But if you look for a master degree in science education, there are just few of them, in Naples, in Bologna, in Roma, and in Pavia. So this is our master degree curriculum in didactics and history of physics. And since we are within physics department, I think you can imagine that sometimes we have some tension with our colleagues who just doesn't care about education. They just care about their stuff and doesn't consider at all education, especially in science, as something worthy to spend time and money. So we are dealing with daily tensions, but we are growing and we believe in what we do. So, and also some words about becoming teacher in Italy. It's very hard. I mean, and that's another big difference compared to your situation. Because if you want to become a temporal teacher, you don't require a title, because there are plenty of positions open because teachers are missing. We lack teachers, especially in science subjects. So even undergraduate students are allowed to make substitutions. But if you want to become a permanent teacher, you have to take a bachelor and a master degree in your discipline. You have to take additional exams in psychology, pedagogy, anthropology, and didactics. Then you have to win a national competition, and it's very hard to win. And the competition is made of 3 steps: a written text, then a practical part, and then an oral part, when you are supposed to imagine and try to present an example of instruction about some topic that you select just 24 hours before to make the presentation. So these are just numbers of the latest competition in our region. It is a national competition, but is divided according to the regions. So my region, I participated, we were 153, 10 positions allowed, just 10, and they were extended to 35. And since the competition are not made every year, they are very difficult to pass. The last one is the eldest person that was participating in our competition the last time. So more than, about 60 years old, still not permanent. So you can see the difficulties and the bad things that are coming. So as a consequence, many of the physics teachers do not have any kind of science education formation because they're not allowed, they're just asked to take some exams. They're not necessarily asked to compensate this lack of competencies. And also teachers more focus on provide students with knowledge rather than guiding them through learning where their views and ideas count. Because that's our consideration also of the teachers, as you can see from the National Competition Organization. Then I will pass to our Bologna research approach to science, especially physics education. Physics, because we are all physicists as backgrounds. We are about 15 of us, and except from the 2 persons that got graduated in master, we are all physicists. So these are the projects we were doing and we are doing at the moment. They are mainly Horizon 2020 projects that are basically a kind of funding from the European Commission, and you see the periods. At the moment we are finishing the Fedora one in August, and we just began the Claim Academy. All the projects are made with foreign partners within the European Union. So, and what are the key points and objectives that are shared between all across all our projects? Our aim and our starting point is to pursue a scientific learning that could be for students relevant, meaningful, and authentic. because we see many of the times we interview students, they feel like physics and math and science as something very far from their lives and something not useful to their development as people, as citizens, and so on. For many reasons, we will try to get in some of them, but especially so what we want to, transform our learning in something relevant for students in the terms that they should feel that they are learning something close to them, meaningful, so students should feel that they are learning something engaging to them, and authentic in two ways. So personal authentic, so they can put their ideas and views in the content learning, and also scientifically authentic, because we have to stay within the disciplinary boundaries, so work on the detachment between school and practice and scientific practices. Because as you can see, often what happens is that the school that you learn, the science that you learn at school is very different, is very detached from the science that you see around, you see in things, in the engines of your daily life, so you cannot figure it out what is meaningful, your science education at school for what. So our process is a kind of 3-4-ish step process. So we start when we want to develop an instructional activity, a module of some scientific and physics content to work on the discipline. So we start all the times from the discipline, because we are physicists, we have to deal with physics teachers. So we appreciate the value of the discipline. We recognize that there is so much in the discipline that can become a tool for the students' development. So we start with them. Then we develop teaching practices, and then our aim is to develop teaching practices that can allow students to appropriate the science content. And as soon they can appropriate, of course, not everybody can appropriate, someone, just someone or whatever. Our aim is to shape this kind of teaching process as something that can be useful also for the personal identity development. So that's my focus research. I will explain you later. So what do I mean for working on discipline? We much rely on this theoretical framework that is model of educational reconstruction by Renders do it. So when working on the discipline for us, it means to study the knowledge and construct appropriate design principle, respecting the disciplinary authenticity and exploiting the productive forms of complexity of knowledge. So we start from the content, and the process we have to face is, if we want to present this content into the class, we have to transform this science content into science content for instruction. So science is not something given, that's our starting point. It's something that you can reshape, staying within the boundaries of the discipline, but you can reshape and gives new flavor and allows different dimensions of the science content to emerge in order to fit into the context of learning. And then there is after the construction or reconstruction of the process, we have to find out how to pursue this, and it is through these design principles. For example, these are examples of design principles at the basis of a thermodynamics instruction. So enhance the multi-perspectiveness, the multidimensionality, and the longitudinality of science. If you see thermodynamics, we can conceive macro thermodynamics or micro thermodynamics. So enhancing these different dimensions and these different perspectives allows us to present a content that is more broad for students, and so it's more easily to find a different positioning that are more close to the personal taste of the students also. Second, developing teaching practices. So what does it mean to develop teaching practices for our research group? We have to develop teaching practices match with the new shape of the knowledge content that we have constructed in the previous step. So if, for example, we want to allow multiple position within the content, we want to highlight a multiple position within the content, we have to, for example, develop some activities where we ask students to consider and to put themselves into multiple positions and multiple perspectives, and then look at the science content through and from these multiple perspectives, and so on. So basically, we have to set the condition for students to position themselves towards the content and within, of course, the disciplinary boundaries. That is our goal within this two-steps process. Because we believe that, of course, math is not an opinion, and that they were telling me a lot when I was a student, but at least science is telling us that within the content, there are many opinions and perspectives still in debate. For example, the debate between quantum mechanics or general relativity, the dualism of the light, or for example, the historical debate between Bohr and Einstein, and then also the EPR experiment about what is the truth, quantum mechanics or hidden variables interpretation. So allowing these that are part of the history of science and the daily practices of science, we allow students to see that they can have an opinion when they are learning science. There is space for opinions when learning science. Okay. Then appropriation. So the reconstruction that we have done toward a more rich and open knowledge can allow students to content appropriation. What do we mean for content appropriation? They have categorized, my advisor and their colleagues, appropriation in 5 categories. So you are supposed to appropriate a content when you can see that students' discourse is, for example, an expression of a personal signature idea, and is grounded in discipline, and it is thick, so it involves a metacognitive and epistemological dimension also. It is not incidental in the sense that you repeat and you keep on going with your positioning when talking about this content. And it's also carrier of social relationship, in that it positions the student within the classroom, because that student, for example, has a taste of for the discipline, and he likes to position in the macro perspective of thermodynamics. The other students just like the micro perspective of thermodynamics, for example. So this can position students and allow also to develop a positioning and so also a science identity within the classroom. So towards Fedora, that is our project. My main project, my PhD research is framed within this project. You can see that we started from relevance, meaning, and authenticity that are objectives of our instructional activity. Then we have to respect our boundaries, conditions, so disciplinary grounded teaching, specific class practices, and develop appropriation through learning as instruction steps. You can conceive them as instruction steps to reach the shape that we gave to our research projects. For example, Fedora. Fedora is future-oriented science education to enhance responsibility and engagement in the society of acceleration and uncertainty, and is funded by Horizon 2020 program by European Commission. So these are our partners. We are leading this project as the University of Bologna, but we have also colleagues from Kaunas Technology University in Lithuania, then also University of Helsinki, Oxford University, and these other two, Teach the Future and Formica Brew, are external partners. So, Fedora project, what are the aims? It aims to work on the detachment that you can perceive between science at school and science outside school. So students, as I said before, feel this detachment, and actually there is a detachment in terms of design of curriculums, topic addressed in the classroom, the practices that you make in the classroom. For example, you don't make so often in our classes like peer reviewing, like questioning ideas, developing ideas by confronting each other. You just learn from the textbook. So that's really different from the real scientific practices where you have to deal with colleagues' ideas, we have to argumentate your discourse on something and so on. So this is the objectives, and the way we are doing is grounded on 3 blind spots: the search for new languages, an interdisciplinary approach, and the need to futurize science education. So, the new languages. Why the new languages? Because, as you can imagine, sometimes the disciplinary language is not enough. Because it's respecting the disciplines, but at the same time it's kind of excluding different positioning, different tastes for students. It can be an obstacle to get in touch with science, the formality, the structure of the science discourse sometimes. So we don't want to betray the language of science, but we want to enhance by adding some other languages. For example, we want to merge the language of physics with other languages coming, for example, from art, to enhance the meaning of science content itself and provide multiple access points. I was in an activity with a teacher some months ago, and she said this about an activity when we were merging physics with writing. I almost feel like I can consider the language of writing and writing as the rhetoric of physics. And that is very nice, because even writing itself, even that very language needs rhetoric. So anyway, a code that goes beyond the word itself to better express concepts. So you use other languages as a scaffolding to bring to the students the science content itself. Then why interdisciplinarity? Because if we see all the stuff around, we cannot see that phenomena can be categorized within just one discipline. If you want to learn about artificial intelligence, for example, artificial intelligence comes from very different backgrounds, from physics, from informatics, from technology, and so on. So, since the innovation is not disciplinary categorized, we want to dismantle the kind of silos effect that we can see within science education at school. So, try to go over these boundaries between disciplines. And finally, to futurize science education, because we see a kind of discrepancy between the atemporal teaching approaches and the need to support students to construct visions of the future by empowering actions in the present. So trying to develop activities which fosters future scaffolding skills. So these are examples of activity. These are all the activities that have been made so far within federal projects. You can see there are many of them. Some of them have been repeated more than once. And they all are grounded upon those three pillars that you have seen before. For example, in the Quantum Atelier, at the bottom right, students were dealing with the second quantum revolution concepts. And then at the end, they were asked to try to represent, guided by the art teacher and the physics teacher too, to find a way to represent the concept of quantum technologies within art products and art artifacts. Or for example, in these activities, Kairos, this is one I'm dealing with very close. Students are merging physics of complex systems with writings. So writing a theatrical piece. So I'm framed within this project, Fedora, with these aims and with this ambition, this tradition. But my focus that I want to pursue is to study and to take a perspective about disciplinary identity development. So it all started, my interest in science identity, when I was doing my master thesis 2 years ago. I was studying the community of practice theory by Wenger and Leib, and I encountered this concept, nexus of multi-membership. And so the nexus, maybe you know it, the nexus of multi-membership is a place where the people can be represented. Is a metaphor of the sense of belonging to multiple communities, so to being in the development of multiple identities as multiple sense of belonging. So I was starting with a personal, I have to admit, with a personal question. What was the contribution of physics in forming myself? And I didn't know how to answer. So I wanted to be capable to answer this question, not also to me, but also to all the other students, because I feel like physics had a strong impact on my life. So I decided to start with identity research, that is a trending topic. You can see in the latest 30 years is increasing a lot the studies. They are increasing a lot the studies on research, on identity research. And they are different in many ways, so you can see different examples in terms of conceptualization of the identity, in terms of research methods, in terms of the aims of the research. But what I noticed is that, okay, maybe later. So, what is my positioning with science identity? I navigated through the literature and then I found this approach to science identity, that science identity and identity, of course, is not something given, but is something that can be conceived as a trajectory, a spatial and temporal trajectory, so something that the individual is constantly negotiating and between himself or herself and the others around him within the community of practice. So, not identity as a phenomenon, but as something that is continuously evolving. And then I saw, and you can see also in the literature, that science identity is mainly conceived and conceptualized as an operational lens to study other issues, for example, power structures and politics of recognition, learning programs, and so on. And you can categorize in order to develop your identity with some categories that you can build. These are the most used: the sense of competence, the recognition, the performance, and the interest. So you use these categories to frame the science identity development for students, for teachers, and so on. But what I just started to see, navigating through literature, is that there is a kind of huge homogeneity of the studies dealing with science identity. They all try, not all, but the most of them, they are looking to study how the experiences of performance, so the categories you have seen before, recognition and competence, within scientific learning can sustain or inhibit the personal identity development. So you can see that these studies just focus on the socio-political dimension of the communities of practices, for example, of physics, of biology, of chemistry, because they study the interaction between people, the politics of the power, the structure of the power, the politics of recognition, of inclusion, and so on. Very few studies, on the other side, are looking how the experiences of the discipline features in terms of the epistemology, the scientific practices, and the methods can sustain or inhibit personal identity development. So, very few studies are posing the question how the features of the discipline itself, how the feature of mechanics or thermodynamics or so on, can inhibit or sustain personal identity development. So these studies can be focused on an epistemological dimension. Because we see that sometimes, as I said at the beginning, students see that physics, the epistemology, the substance of physics is not so relevant for their development. But at the same time, when I was doing my interviews in my master program, many of the students, they were saying us that physics, in some sense, they felt like they had provided them not the social relationship between a community of physics, the sense of recognition, but the forms of the disciplines. They have provided them with some instruments, positive or negative, but with some impact on their development as person, on their mindset, on their structuring as citizens. So our aim, my aim of my research problem and my objective is that, of course, I want to take consideration of also the perspective that are dealing with social scientific structures informing science identity, but at the same time I want to try to develop a theoretical construct from data collection and analysis which may help in understanding how the disciplinary epistemological features can inhibit or sustain students' personal identity development. So, in order to do this, I need to ground my research on theoretical frameworks. One theoretical framework I use and we use within our research group is this FRA reconceptualization. So these authors, Erdogan and Dagger, they are within the strand of nature of science, But the interesting that they are doing to us is that they are constructing an image of the disciplines as composed and combined by different parts that can be clustered into two big pieces. One big piece is the core, that is the cognitive epistemic part, and the other big piece is the external ring, that is social cultural part. So when you speak about disciplines, you have many dimensions in disciplines. You have the social interaction, you have the power structure, you have the inclusion, you have the gender issues, but you have also the practices of doing science, the knowledge, the methods of doing science, the aims of doing science, and so on. So, of course, we cannot separate them because they are all combined in forming the disciplines as a whole. But we can concentrate at least on the core and see what kind of impact the epistemological part of discipline can have on identity development. Then I grounded myself, as I already said before, on this other approach when developing instructional activity. So, given my aim to deal with epistemology, I have to ground on a framework that allows me to deal and reshape and give you new identity to this epistemology according to the classroom I want to go. So I took the example of the model educational reconstruction. So my research question in the end is that what epistemological types of knowledge and what kind of educational reconstruction leave room for the development of personal identity in physics learning. And the way I'm trying to address this question that is, very broad and ambitious, is that I keep going, designing activities, collecting data, analyzing them, in order to take trace, if there are, of course, of all the local ways and all the local answers that show us a kind of contribution to this objective. So all the local traces between that are enhancing a kind of relationship between the epistemology of physics on one side and the identity development, the personal step, the identity work of the students, the self-construction. So I will present just a brief overview of two examples I've been involved in about educational reconstruction. Fisica delle nuvole and Kairos. Okay. Kairos, maybe you know, is a Greek word whose name is, its translation is time, but not the normal time, because time can be translated in chronos, kairos, einautos, eion. Greeks used to have many words because you have different issues, nuances within just one concept. Kairos is the time of the destiny, the time of the fate, the time of the chance. So we decided to reconstruct the physics of complex systems. So we decided to bring in the class the physics of complex system. Why? Because we were thinking at that time, 2 years ago, and now, because we are doing again, that the epistemological structure, that is our starting point, so the epistemology of the physics of complex system can be a source due to its richness, because you have very deep concept within that. Can be a source of words and epistemic forms of reasoning that can stimulate critical and systemic thinking needed to navigate today's society. So dealing with them can train to understanding the complexity of systems around us. And so this concept, treated in some perspective that I will describe, can help to build conceptual structure for students, models or metaphors to orient oneself in today's society. That is a society that is accelerating and accelerating and accelerating. So this is, we were just summing up in one day with my master students and my advisor the whole process from the choice of the content, then the study of the content through the manuals, then the choice of what experiments bring into school, what concept bring to schools, how do they then, with what aims. So this is what we mean by educational reconstruction, okay? And we like so much blackboards, so we were doing that in the blackboard, the old way. So, two examples, as I said. La fisica delle nuvole, grade 9, 3 years ago, we chose to present the basic concept of complex system. And students, that the second part of the module, I will explain later, but just a little spoiler. We have said that we want to merge different languages, okay? So, the physics languages through the concept of complex system, and then another language to enhance this meaning. And we were choosing, because we were in our team another teacher, a literature teacher, we were choosing the language of writing, okay? So creative writing. And then we are doing again with grade 10 in these months the same stuff as before, but we are adding some more concepts. I will explain you in a minute. And we are adding also laboratory session this time. So in the first time, the students were asked to attend 1 hour each lectures on complex system and their properties, concept, as I said, chosen and reconstructed by physics teacher upon a model of educational reconstruction approach. So examples of the concepts presented were circular causality, deterministic cause, emergent properties, irreducibility, and so on. As you can see, since they are grade 9, we cannot go that much into the math stuff, because just grade 9, they are very young, and this kind of physics is very complex. You study at master level. But we wanted to construct the meaning, to report the meaning of this concept. I mean, their depth, their broadness, in some sense. In the second implementation we are doing, we wanted to enhance those concepts, but also to add something, a special highlight to the emergent property. In physics of complex system, you have that the interaction at the lower level can provide an unpredictable emergent behavior as a whole system. So we wanted to highlight this concept in terms of spatial and temporal structure emerging through a chaotic and dynamics and behavior. So, from the spatial and temporal patterns that can emerge, it is possible to extract some key concepts of complexity paradigm that have been shown to generate new knowledge in their diverse disciplinary fields. So, why we wanted to highlight this emergent? Because the emergence that has been reinterpreted as a metaphor for studying all and interpret other phenomena, like in social science phenomena, like in philosophy and so on. It gives us, and also the students, the idea that even if we are within a field very clear, that is physics, we can go out from physics with that content and use that content as a metaphor, as a lens to interpret and develop new knowledge outside the content, outside the original field. Then, as I said, we added 2 session laboratories. One is about the Bénard cells, and the other is about the BZ reaction. So they are a phenomenon that occurs in the physics of complex system. The Bénard cells are cells, these are pictures from our interpretation. These are cells that are for emerge when you apply a gradient of temperature to a liquid, under some constraint, and when you reach a threshold, you start to see cells forming, and so a spatial structure that is emerging. So we wanted to highlight the emergence of something, so spatial structures are emerging. The other is an oscillatory reaction, so you just add reagents in a beaker, and then if you keep on stirring the reagents, you see that it emerges a period in the colors. So the solution changes colors according to a period. So this is another structure, a temporal structure, that is emerging. So 2 structures, temporal and spatial structure emerging. We don't know why, we don't know how. I mean, we can see how, but for students, we don't know how. We just know because of the local interaction. So we wanted to highlight this process. From the interaction at the local level, you see macro events coming. So some consideration of this. starting from a condition in which there are no space-time structures, because if you don't steer, there is no color. If you don't hit, there is no structure. We see the emergence of space structures or time structures. So both processes can be interpreted as bifurcation from an unstable state into two new stable states, or three new stable states in the case of colors, which finally led to a chaotic regime as a superposition of space and time patterns and so on. Hence, so the bifurcation, which defined the emerging space-time structures, it becomes, when described and faced in this way, as an analytical tool used to study other phenomena. We see that, for example, bifurcation can be used, and then has been used as a lens to interpret the opinion dynamics in social science, for example. And so it can be used also outside the original discipline, that is physics. So that's what we mean for educational reconstruction. To show scientific epistemological features, so go into the concepts of the physics, study them with the students, translate them outside the discipline, so providing them examples of how they can be lenses for other things, reporting and enhancing their meaning through new languages, so working on the new languages, ensure their potentialities as analytical tools in other contexts, but also for personal tools. So in the second part of these activities, we were asking students to write something, guided by the teacher the literature teachers. So they were asked to set the stories, to write stories in group or personally in this new implementation, to write stories that are set within a complex system, to refer these stories in some sense to the epistemological features that we have discussed and co-construct together in the classroom, and also to deal with the narratological constraints with the narrative language. Okay? So what do we mean for narrative constraints? The teacher guided them in using different narrative sequences, in choosing and constructing a beginning sequence and an ending sequence, in making use of some narrative techniques borrowed by famous writers that have been dealing with complexity. For example, Italo Calvino is one, or other things like how to insert the humor in a story. So things that are coming from the literature, but we merge it because we have to refer, the content is provided by the physics of complex system. So writing as a kind of betrayal, because when we write, we have to take the concept out of the field, because we have to represent them through another language. So it's a kind of betrayal, because we don't use formulas, but at the same time it can be an empowerment of the complexity meanings, because if we want to describe something, like in poems, if you want to describe something, and you describe something many different ways, through a formula, to a painting, through a description, you enhance the meaning of that concept. Okay, so that's our aim. And what we found in the first implementation, we are waiting for the analysis of the second one, is that students, through this process, wrote the stories and respected the narrative constraints, reported the features of complex system and so on, but also they reported something personal through the voices of the characters and through the thoughts of the characters. So, and this was new to us, because we didn't ask them to talk about themselves, but this process, in some sense, gave them the chance to report some personal demands that they were unconsciously willing to share, in some sense. So we analyzed them and so on. I don't want to go through the detail. We can do maybe later if you want. But through an analysis, qualitative analysis, we found out that one big demand was coming in a systematical way, because in all the essays this tension was coming, and this was totally unpredictable at the beginning, because the metaphor of complex systems, scaffolded by the use of this tool of creative writings, allows students to express a personal particular need. The tension between them, the self and the group. Because in complex system you have the interaction between the single agents, so you have a look on the agents, but you have a look also at the system because you have different behaviors. So this is a metaphor that they have been used, and they are talking and they are confirming us, as you can read on the right, because we met them 1 year later. We talked about those essays, and they were saying that, of course, this we realized that in some sense these instruction activities gave us the opportunity to talk about themselves, to put ourselves into the cloud, because we, for example, one character was a cloud, and talking about themselves, about ourselves when describing and talking through the cloud. So we see this activity as a practical example, for example, by which, acting on the content reconstruction and not only on the instructional strategies, it was possible to open up space for students' expression, to give voices and images to personal demands and needs. So reconstructing epistemology authorized students' identity to emerge, but at the same time, we see this epistemic identity works. So we see these steps in the construction of the selves, that is, for example, the expression and reconceptualization, getting more aware of this personal tension, as steps that are inspired by the learning of knowledge structure. And this is our main finding. Now, I don't know if I have more time, just 2 minutes spending on what we have done also with David. This is a total new chapter of my research. David was visiting last year, as he said, so we tried to implement this framework. I mean, this framework, ambitious science teaching, you know way better than me, in Italy, with a master student, but in some sense it's still related to our objective. We wanted to see how the implementation of this framework can enhance this identity development, appropriation that we are trying to study within our research group. So we did with pre-service teachers, we did within 6 lectures. They were informed about the AST practices, they studied the framework, but they also were asked to go through the kind of instruction informed by ambitious science teaching forms. So they were at the same time pre-service teachers studying some literature, but on the other hand, they were like students, and we were the teacher, me and David, trying to follow in the steps of the ambitious science teaching. So guiding them through the making sense of an anchoring event, expressing ideas, eliciting ideas, constructing models. This is the event that we chose. I chose the synchronization of metronomes. Maybe you know it. These metronomes got synchronized because of many reasons, but especially because there is the table that is guiding the phase to couple around just one value, mean value, that is described by the Kuramoto model. This is a model of coupling oscillations. And we were asking students, of course, to follow the steps of ambitious science teaching and so on, to build their explanation models. And we have also 2 research questions, because this was made also within a master's student thesis I was advising at that moment, one master's student, Michelangelo Panza. And these were the 2 research questions we were trying to address through this process of inquiry. So after the module, we analyzed the model, we analyzed what happened in the classroom, we developed a questionnaires and some interviews. I go fast here because I just want to focus on this, that going through the interviews and going through the question, we wanted to see what was the impact of a total new framework, because students are not accustomed to learn like this. To go through an anchoring event that they don't know which knowledge can be used to explain that. So they have to just try, develop new ideas as they were scientists, because scientists does this way. And we were interested in, got to see how the students were positioning towards this new kind of teaching. So in a sense, they accepted, they understood, and they also appropriated this framework. And what emerged is that at the same time we have these two levels. So the real scientific practices that emerge according to this implementation framework, because students were asked to develop their explanatory models, to making peer review of the other model, to explicit ideas, supporting those ideas by argumentation and so on, gave the chance to act on the knowledge. And at the same time, the safe place, because the condition was very safe, you know maybe how David behaves in the classroom, so very inclusive settings and so on, set the students as the agents. So in this dualism, there is a compensation of two possible criticalities, because on the one side, students were kind of, they were feeling fear, because the phenomenon they were asked to explain was totally new. So they didn't know how to explain that. But this fear was compensated by the safe place, condition. And at the same time, the epistemic scaffolding given by the scientific practices filled the classroom discourse with meaning and scientific knowledge. And so something interesting was expressed by students and in analyzing their interviews and addressing our research question. So the framework was accepted, and but also explaining how the framework goal of epistemic outreach was achieved thanks to the dualism of safe place and scientific practices, as I just said to you, but also that we saw that displaying how working with the real scientific practices at school, so dealing with ambitious science teaching framework approaches and so on, it is possible because the students were telling us that through going through the real scientific practices that are embedded in this framework, they were feeling that they were kind of approaching more into the science outside school, kind of approaching to real scientific practices. They were recognizing the aim of the framework, so they were in a way reducing the feeling of gap between science at school and science outside school. So in a way, they develop awareness and on this gap, and at the same time they reduce in a way. And this is the end of this work. We are trying to see maybe if there is some implication of the futures. And I would just to end this presentation with this. Today in Italy we have a national holiday, and it is the day when Italy got freed by the fascism in 1945. So all my families, all my friends are celebrating there. It's maybe the most important holiday festivity. It's very important because it became the starting point for our republic in Italy. So I want to say thank you to you for your attention, and also thanks to these men who got freed, who freed Italy in like 8 years ago. About. Thank you. Okay, maybe I used too much time. I am sorry. Okay, any question? I'm here. Comments, doubts, explanations, insults.
So yeah, I have a question, or maybe you can comment on. So sort of back to maybe some of your research questions about science identity.
Yeah.
Obviously students have encountered other science courses coming into the 10th and 11th grade. To the degree to what, in Italy, how much of that would be physics experience? And then I just wonder, have you thought about their previous experience? Certainly these units you're teaching them, or modules, would seem probably pretty drastically different than their previous science learning experience. So how does just the engagement in the module itself may change their perspective of what science is, based from their previous experience?
I mean, of course, this is a total new experience for them.
Yeah.
We are trying to working with them. We involve also their teachers. So we come with the physics teachers who is doing this is a retired teacher, so he's not the teacher of the students, but we involve also the actual teacher. So the teachers that taught them also in the previous years. So there is a kind of, he makes the role of connecting ordinary lectures with these extraordinary, let me say this way, lectures. So it finds that experience a place as a kind of extraordinary event to participate in, to engage in. So I think that is important, because we don't want to appear like people coming from the university and doing something that maybe is totally irrelevant to you, not accepted by the teacher, not requested at all by the school and so on. But we want just to try at the disposition. I mean, I do not teach in these activities. I just been involved in the previous step, the reconstruction. So I go through the topic, I study it, I reconstruct, I choose with also my colleagues what to present and discuss in classroom, how to do this. And then we put this material at disposition to the teachers, so they can try to make a kind of conjunction to the previous experiences too. I don't know if I replied in some sense.
Just maybe a comment on like what maybe more, even more generally for high school students, what is their science identity even in high school, or from physics, what would be their background or experience or even identity with physics?
Grade 9, they do physics for the first time. So I don't know if they have physics identity. Maybe they have science identity.
Yeah.
Maybe they also don't know which kind of science identity they have. But I mean, our position is not to see what kind of identities they have, because we don't want to say, you have this kind of identity, so go there, you have this kind of computational identity. We just want to, okay, you can construct your identity as Francesco, as Mark, and as a person. This is physics. This can be helpful for your identity, okay. If it is helpful, take it, whatever, doing whatever with this content. Use it as something special for example, for expressing attention between you and the group. So we do not rely that much on previous identity, because we don't want to see identity as something already there. So I can see your identity is constantly evolving. I mean, that's our position.
I had a question regarding the complex system aspect. So, what were the challenges like that you noticed in students while getting, and what were the also strategies you used in the unit to really, in a way, to convey and explain students the different aspects of the complex systems?
Yeah.
What was there at all such an explicit introduction, and if there was, what was it, and basically also what were, if at all, what were the challenges with regards to introducing complex systems to the students?
I mean, the main challenge is that complex system physics is telling you something very different from what is telling other kind of physics, like for example mechanics. Because mechanics, you set the condition, you know the initial position, the initial velocity, you see what is gonna happen. In complex systems, you set the position and you still do not know what is gonna happen, because we have deterministic chaos involved. So the difference is huge, as you can see. So one challenging was accepting this, because my physics teacher always told me, okay, this is gonna be the evolution of the system. So I can rely on the evolution. if we dismantle this concept of keeping tracks of evolution, that's a challenge. Okay. The other challenge is to have the ability to develop the instruments by which to look at the complex system. And we use, for example, net logo simulation, maybe you know, in order to give a representation, because it's not so easy to develop in your own mind, emergent behavior. What are emergent behavior? What are emergent properties? So we give a representation to help us in transmitting students our conception about these what we mean by emergent behavior. We did also with the experiment labs. So what do you mean by spatial structures emerging? It is like this, like the cells coming out when you heat the liquid. So these were the challenges. And another huge challenge was to merge the two languages. So students, at least in that grade, but also in later grades, they are used to switch. I mean, when they are in the Italian class, they think just with that instruments. When they go to the physics class, they just forgot they just leave all the stuff out of the door and just use the formal language of physics. So the difficulty in our sense was to let them merge the two languages. You can use different languages. You are not supposed to think just according to the place you are. I mean, innovation works like this. You merge people with different backgrounds. You talk each other using different languages. So it's very powerful, but they don't teach you at school. I mean, in our school, we don't teach that much. So that was another challenge. Why you are asking me to use physics within the Italian literature class? Am I supposed to use physics concept when writing? Why? But in the end, they managed. In the end, they managed.
Okay. It's time. All right.
Thank you.
Thank you.
Thank you.